The evidence of the existence of discrete energy levels in an atom is the emission of line spectra by atoms. Click the hydrogen button and then the helium button to observe the line spectra of hydrogen and helium. Introduction to line spectra of hydrogen. In this lesson, you will learn to use the equation for En to calculate the various energy levels of the hydrogen atom, to understand the concept of excitation energy and ionization energy, to use the concept of transitions between energy levels to explain the emission line spectrum. The equation shown represents the energy levels of the hydrogen atom using the Bohr model. For hydrogen, Z equals 1. Click the calculation button to determine the energy level of the ground state E1. Click the Allowed Energy Levels button to deduce the expression for the nth energy level in terms of the ground state energy level. Now click the Next button to calculate the next 3 energy levels. An energy level diagram may be used to represent the various energy levels of the hydrogen atom. Click the Energy Level Diagram button. At any instant, the electron in the hydrogen atom can only be orbiting the nucleus in one of these energy levels. Summary. The various energy levels of the hydrogen atom is En equals minus 13.6 over n squared electron volt. The various energy levels of the hydrogen atom may be represented in the energy level diagram. At any instant, the electron in the hydrogen atom can only be orbiting the nucleus in one of these energy levels. When the electron is at an energy level higher than the ground state, the atom is said to be in an excited state. For an atom to be excited, energy has to be supplied. The energy required to raise an atom from the ground state to an excited state is called excitation energy. When the electron is in the energy level for n equals 2, the hydrogen atom is said to be in the first excited state. When n equals 3, the atom is then in the second excited state, and so on. Click the Excitation Energy button to view the excitation energy required for various excited states. When an atom gains enough energy for the electron to leave it completely, the atom becomes ionized. The electron now becomes a free electron. The minimum energy required to remove an electron from the ground state of an atom to infinity is called the ionization energy. If the energy supplied is more than the ionization energy, then the surplus energy becomes the kinetic energy of the free electron. From the energy level diagram, deduce the ionization energy of hydrogen atom. Click the Ionization Energy button. A hydrogen atom can be raised to an excited state or can be ionized by collision with an electron or interaction with a photon. Consider the collisions of a hydrogen atom in the ground state with electrons of different kinetic energies. Click on each of the energies of the incident electron in the table and observe the possible transitions of the electron in the hydrogen atom. Click the Reset button before clicking on the other energy. Predict what will happen if the incident electron has energy higher than 13.6 electron volt. Answer: the atom may be ionized or excited. A hydrogen atom can also be raised to an excited state or can be ionized by interaction with a photon. Consider the interaction of a hydrogen atom in the ground state with photons of different energies. Click on each of the energies of the incident photon in the table and observe the possible transitions of the electron in the hydrogen atom. Click the Reset button before clicking on the other energy. You would have observed that the hydrogen atom only absorbs a photon whose energy is exactly equal to the difference in energy of two energy levels. The atom cannot absorb a portion of the energy of a photon. It either absorbs all the energy or none. Suggest other ways in which an atom can be excited or ionized. Answer: collision of atoms with one another, such as in a flame. Summary: the lowest energy level of the hydrogen atom is minus 13.6 electron volt. For the nth energy level, En equals minus 13.6 over n squared electron volt. When the electron in the hydrogen atom is in the lowest energy level, the atom is in the ground state. The ionization energy of an atom is the minimum energy required to remove an electron from the ground state to infinity. An atom may be excited or ionized by collision with an electron or interaction with a photon. The electron in an excited hydrogen atom would only stay in the excited state for a duration of a few nanoseconds. The electron would then jump down to a lower energy level. According to Bohr's theory, the frequency f of an emitted photon is given by hf equals ei minus ef, where h is Planck's constant, ei equals energy of the initial state, and ef equals energy of the final state. The wavelength lambda of the photon is given by lambda equals hc over ei minus ef, since c equals f lambda, where c is the speed of light. Click the Electron Transition button to view the transitions of the electron from the various excited states to the ground state in the hydrogen atom. Calculate the wavelength of the emitted photon in each transition. Click the wavelength button to check your answers. State whether these wavelengths are in the visible range. Answer: no, they are in ultraviolet range. The wavelengths of the emitted photons due to the transition of excited atoms to the ground state result in the Lyman series. Click the Lyman series button. The Balmer series is observed when the electrons make transitions from n greater than 2 to n equals 2. Click the electron transition button and the wavelength button. Click the Visible Spectrum button to view the visible part of the Balmer series spectral lines. Besides the visible spectral lines, there are also non-visible lines in the Balmer series. In which region of the electromagnetic spectrum are these non-visible lines? Answer: ultraviolet region. Click the Lyman series button to view the Lyman series in the line emission spectrum of hydrogen. Click the Balmer series button. Click the Paskin series button. The Paskin series of spectral lines are observed when the electrons make transitions from n greater than 3 to n equals 3. These spectral lines lie in the infrared region. Click the Spectral Lines button to compare the wavelengths of the 3 series. Summary: transition of electrons from a higher energy level to a lower energy level produces the emission line spectra. When a beam of white light from a filament lamp is incident on a diffraction grating in a spectrometer, continuous spectra are observed. Click the Continuous Spectrum button. When a beam of light from a hydrogen discharge tube is incident on a diffraction grating in a spectrometer, the emission line spectra of hydrogen spectra are observed. Click the Emission Line Spectrum button. Click the Absorption Line Spectrum button to observe what happens when white light from a filament lamp passes through a hydrogen gas before it is incident on a diffraction grating in a spectrometer. Notice that the positions of the dark lines in the absorption spectrum of hydrogen are the same as those of the lines in the emission spectrum of hydrogen. Hence, hydrogen atoms absorb photons of the same frequencies as those that they emit. Summary: an absorption line spectrum of hydrogen is observed when white light passes through a tube containing hydrogen gas. And hydrogen atoms absorbs photons of the same frequencies as those that it emits.